This is review of Unit 7 and some of the Unit 6 stuff for the test. It's the stuff I would write down. The first thing we did is, we did UV substitution. This is going to be on the test, and this is in the review. And how do you do UV substitution? You do this right here. This stuff. It's this formula right here. UV substitution, ultraviolet voodoo. Now, the key part of ultraviolet voodoo, you got to figure out what you're plugging in for the U. And we use this acronym LATE. Look for the natural log part. There's no natural log. Look for like X polynomial parts. X's or constants. Could be that. There's no algebra. No polynomials. Try some trig. Exponential would be the last one, but you don't want your E, that to be your E's, or that to be the U. You have to pick a U and dV, and you go from there. The formula to know is this: ultraviolet voodoo. Ultraviolet voodoo. Voodoo. Whatever. We pick, we go from there. That's what's to remember. The next thing we did, partial fraction. So partial fraction was about, hey, how do I take something like this and decompose it to like 1 over x minus 4 to like this? Because I can integrate this. I can integrate something like this because each one of those would just integrate to the natural log of x minus 4 minus natural log of x minus 3. But I cannot integrate this thing as is. So we had to break it down. Now, how do you break it down? We had some steps. It was a long process. But look at your notes on how to do that. Have those ready. That's what you need to do. Part of the AP test. I expect it to be on the AP test too. So, and it will be on your test. And it's on the review. The next thing we did was improper integrals. So improper integrals are when you do stuff like this. You have this problem. Oh, I can integrate from 1 to 8. But then I'm like, what if I integrated from 1 to infinity? And I want to find the area under the curve. Well, what are the rules? What changes right here? Improper integrals are any times we have infinite limits or negative infinite limits. Or when there's a discontinuity at the endpoints of the limits or between the limits. So this is obvious. I got some infinite limits for each of these. But if you divided by 0, that would be an infinite discontinuity, a vertical asymptote. In this case, 1 would divide by 0. You plug in 1 here. So that's why we call it infinite or improper. In this case, I go -2 to 2, and that's fine. But if you plugged x equals -1 here, we'd have an infinite limit. So these are why we have to do improper integration. Now, key parts to understanding in that is your answer might diverge. We did some infinity math. If your answer goes to infinity or negative infinity, and it doesn't like simplify, then you'll say your answer diverges. There really is no answer. So like 1 over infinity, even though it has infinity, that actually we can change that to a 0. So you have to remember that kind of math. Not just because there's an infinity, because some of those might simplify down to an actual number. Same thing if I said e to the negative infinity. That's the same thing as 1 over e to the infinity, which is just 1 over infinity, is just going to be 0. So you got to watch out for those things that reduce to like zeros or whatever. All right. You get infinity, you diverge. You integrate. When you integrate these kind of problems, really the same kind of integration, but technically, sometimes you have to you're really supposed to rewrite these, the limit as maybe not x, as like a goes to infinity. I'm an integral of 1 over a. You'll see this in work being done because can't integrate those, but I hate doing that limit part. I don't really care. Just leave it as infinites. I think that notation's stupid, but it is on some AP tests. Go for it. So you do that to infinity. I hate this part. Just leave the infinities in there, integrate like normal. We've done problems. Go back to your examples on those. Next thing we did, we talked about slope fields and Euler's method. Slope fields is old stuff. You got the little tick marks here and there. That's not really going to be on this test too much. I don't even know if I put one on the real test. I think I have an example problem on slope fields. That's an AB thing. I'm not worried about that too much. I don't even know if slope fields will be on your test. Maybe. But some of the concepts behind that might. But Euler's method, I guarantee that's on the AP test for BC at some point. It'll be on there, and it'll be on your test this week on how to do Euler's method. Euler's method, they'll tell you use Euler's method. That's so you know you have to use it because they'll tell you. The key part to Euler's method, well, it's about approximating using a differential function. Oh, yeah. And so you use this differential function, and usually there's a start point, and I want to get to a certain value. And the idea is I'm approximating by like incrementing my x value and then doing some math to get to the dy dx. If you want to know the lore behind some of this, the idea behind it is your differential dy over dx is approximately equal to the change of y over change of x in our approximation. That's why I get like this math right here. When I say slope, I mean like the dy over dx. So ignoring the lore behind everything, what do is I make this table. X, y, dy, dx, and then delta y, which is equal to dy dx times delta x. And the idea is you're going through, you're going to have some starting point usually, so I'd plug in like a 0, 1. The tip of what I really want to get to is like a final y value. And so maybe I get to like this point here. And you're going across one at a time. You'll start with values here. Okay, you plug in to find your dy dx, boom. Your delta y is this times a, so usually delta x will be given when you're doing these kind of problems, and you plug that in, and then so you'd get 0.1 after doing the math. Now your x will always change by a consistent amount. It's just a step size. So this would be 0.1, 0.2, and then this is going to 0.3. Your y is going to change by whatever we calculate here every time. Since this came out to 0.1, I'm going to go to 1 plus 0.1 is going to be 1.1. Then you keep going. You'll add a different value to y every time till you get to the end. Sometimes I don't give you the delta x in cases. Sometimes I'll say how many steps. So instead of saying 0.1, I'll say, oh, I do 3 steps. And I start at 0 and I get to 0.3, and you do the math and go, oh, well then every step should be 0.1. So sometimes it's presented that way. But you follow the table. That's how I do it. It's just kind of following an algorithm and getting this. If you care about more about the lore, I was thinking about this more. Why do you do differential equations? Why do you have to do this? And certain differential equations, you can, we'll start talking about general solutions. Actually, let's get to the next part. All right, differential equations. This is going to be in the test a little bit. It's an AB thing. It's about breaking apart. So you got differentials because you got y primes or dy dx. It's about breaking them apart and separating the variables, finding general solutions, and finding the particular solutions. If you remember that, that means you have to general solutions. You leave the C in. Particular, you solve for the C. It's the same thing in BC. I have the step process here. We went over that in class. Nothing changed in BC about this, and we'd have to break the variables up. I remembered, so going back to Euler's, there are certain types of equations that you can't do differential, because like, why would you do Euler's and approximate when you can just find the particular and general solutions? And certain equations you can't do that with. That's why Euler's is important, because you have to approximate what the curve looks like. I don't even know if that was important for this video. I just did it. Whatever, moving on. We also talked about exponential and logistic forms. This is probably a mess. I don't know, this felt weird. I'm not really putting this much. I mean, so as a separate thing, I mean, this is more it's just part of being a differential function. It's just kind of like some specialized versions of this. I don't know if this will really appear on your AP test, though. I think about this more. But we went over what the exponential differential function works like. The regular function, like exponential is y equals e to the x, and it shoots up to the moon, just like GameStop. But the differential form could look like this: y prime equals some constant times y, and you can use your, use finding the general solution that we did in the last part. So here's like the general solution form of this, and Sometimes it feels like algebra 2 type stuff. And then we did some problems. There's logistic equations. So logistic you haven't done before kind of look like this. Two asymptotes, which basically means you have a maximum minimum population. It's kind of how diseases and stuff spread. You start off with very few, and then some point get this like crazy growth curve. But there's a maximum population and a minimum because you can't have less than 0. You can't have more than there's 1,000 people in your population. You can't have more than 1,000 that get this. So that's why we have maxes and mins. So this is the general form. This is differential form, which is probably more important for this. But I don't even know. No guarantee it's on the AP test or not in depth that much, I would say. And that's what we did. There's your review.